Welcome everyone, my name is Romain and in this video I would like to present you some of our recent work on modeling and optimizing router energy demand. Over the past couple of decades there has been a lot of work in trying to optimize the energy usage of the core of the internet, the core networks. And in all those works the idea is essentially the same. It's about turning off parts of the network that we don't need when we don't need them. For example, that would be turning off network links when those are not heavily utilized. But all these works, including ours, struggle with the same key question, which is how much would those optimization really save in terms of energy? And they all struggle because in order to answer that question, what we need, and we currently didn't have, is a power model that is fine-grained enough to estimate how much power delta would be induced by those optimizations. And so in this work, we went on a quest to kind of eventually remedy this problem, right? By first establishing a power model that would be fine-grained enough to answer that question, and then using and leveraging this power model to effectively estimate the potential energy savings. So let's get into the power modeling part. Today, and in general, there are two main classes of data, of power data you may find. There is what the datasheet tell you, the datasheet numbers, and measurements you can make. Measurement can be classified into two types. It will be the internal measurements done by the router itself. That will be, for example, through the power supply units that read the power they deliver, or via external power measurements like a power meter. The datasheet numbers are obviously not fine-grained enough for our modeling needs. In most cases, you will find 1 to 2 power numbers in the datasheet. That tells you actually very little about how much power is drawn in practice, because they are not meant to do that. What they are meant to do is give you an overestimate of the power usage so that you can properly size the power supply for your rack or your server room. So the good news is that, as I mentioned, a lot of power supply units, modern hardware, measure the power they deliver to the routers of the switch nowadays. There are some technical difficulties about collecting that data, but that can be solved. However, as we were starting working on this, we met a power electronic prof that actually told us that it was maybe not a great idea to trust the information getting out of those power supply units, which, let's say, was not exactly the ideal information to get. But if it were true, then that means we cannot only rely on internal power measurement, and we need to do external measurements instead. Actually, what we've done is that we've done the two things in parallel. On the one hand, we've been collecting internal power measurement data from the production network of our local ISP and ETH. And on the other hand, we've been deploying some power meters in the network, in the production network, to collect ground truth measurements. So you can see on this image, one of my students, Jonathan, that we're deploying hardware in the switch point of presence at ETH. It led to a side project we called AutoPower. You can find all the links, all the information following this link. So once we have the measurement, we can envision doing the modeling. Modeling routers is a bit difficult because they're essentially black boxes. We don't get to know what's inside, right? The vendors don't want to tell you exactly what hardware is there, how it is assembled, and so on. And it's kind of tricky to directly measure the internal components, right? We need to open the box, you cannot really run them in the state, or you cannot really do it safely. So we're fundamentally limited to a top-down approach, right? To try to measure the entire raw power and try to attribute shares of that power to the individual elements. How do you do that? Well, the methodology is pretty simple. You start from your device or your router on a given state. You measure the associated power. You apply a change in the state, for example, changing the configuration or plugging in a transceiver. And you measure the power again, and you assume that the power delta you observe is entirely due to the state changes you just applied to your router. So what kind of stage changes could we consider? So we start with the base condition, the base state, where the router is powered on, and that's it. There is nothing plugged in, there is no configuration applied whatsoever. Then we start with what we call the idle state, where we plug in transceiver, but nothing is configured. Then we start turning up one of the two interfaces, which will, in theory, activate or power up the service line to that port, but the IP link is not yet up. Then we do the same for the second one, which will take on the IP link, and so the two transceivers will get active. And finally, once we have active interfaces, we can start sending and receiving traffic along those ports. So that's obviously quite a few experiments, and obviously you don't need to just do one of each, right? For the traffic, we need to test with different packet sizes, different bandwidth. We need to test different transceiver types, electrical or optical, with different configuration speeds, for example. And of course, we need to do all those things multiple times to ensure a decent replicability of the results. It's a lot of work, it's a lot of experiment, but most of it can be automated. We've done that work. We've put all those tooling and together, and you can find all that in the corresponding link if you're interested in doing that yourself. From those experiments, we can compile the data down into a power model, which is very simple, that assumes that the transfer power is a constant. And then on the router side, you have a base power, which is the device on its own, plus a static power per port that will depend on the configuration of that port. And then you have the dynamic cost, which is a unique cost per packet you forward, right? Which is correspond to the cost to process the header. And then you have a unit cost per transmitting the bit from input port to output port. In practice, the experiment setup looks like this. We have our router or switch, which is our device under test, that is getting power through a power supply, a power meter, sorry. And then we have a third-party machine, which is an orchestrator that we both at the same time collect the power measurements from the power meter and configure the router or the switch, as well as sending and receiving traffic when necessary. And once you do all the experiment, you process all the results, you can get a power model that looks like this, where you have an instance or numerical value for each of the parameters of the power model I mentioned before. So you can do all this. We have now, on the one hand, our measurement data, right? We're collecting internally, externally, and then we have the model prediction, and hopefully the model will match the measurement. So time to compare. Here is one result or some results on deployment from one run router model. So in red, we have the internal power measurement from the power supply unit. In blue, we have the external one, which is collecting the auto power, which we take as a ground truth. And in green, we have the power model predictions, which are only based on well, the router model, obviously, and then the traffic volume and interface state. And so we see a number of things here. It seems that all three lines, although they are offset from each other, seem to contain the same signal. We have the same daily and weekly patterns that we can perceive in the lines. Importantly, the model captures this, right? We capture the same fluctuations as in the ground truth, and we do see this jump here in the middle of the graph that matches with the other two lines that correspond to a link that was taken down. However, there are also some additional drops, right, in the middle of the plot, which are yet to be explained, but we'll get back to this. The bottom line is, overall, the model seems to be able to capture the power delta that we are most interested in for our need. So we can take that and move to step 2, which is now that we have this model, we can try to quantify how much energy we could save by turning links off. In this work, we use as case study some of our own proposal for energy optimization. It's called Hypnos. The only thing I want to highlight here is that we did the simulation of, or the evaluation of this algorithm on actual real ISP topology and traffic traces, which are publicly available along that link if you're interested in using them as well. The bottom line is the outcome of this evaluation is that Hypnos can turn off about 1/3 of the link on the entire network without inducing any congestion. Right? Now, by applying the power model, we can now estimate how much energy would that save, and the answer is almost nothing. Okay, so why? Well, the first intuition would be if I'm telling you you can turn 1/3 of the link, it saves less than 1%. That would suggest that the link power is actually a very small fraction of the total network power. And it turns out this is not true. I mean, it's not the reason why the number is so small. The reason the number is so small is because when you turn things off, they are not powered off. Right? And that was actually already visible in the model itself. If you look at the TRX power, which is the sum of the power when you plug in and your power when you turn up, you can see that on this passive electrical transceiver, we had already 40% of the power that was paid just by plugging in the transceiver, and only then 60% when it's actually taken up. And it's even worse with the other example, which is an optical transceiver, which, by the way, consumes 10 times more power. Here, 100% of the power gets paid as soon as you plug in, even if the film remains off. And that is exactly what was happening here. Right? Remember, we had this gap here, and by investigating further into the logs of the router, we could see that on that particular day, a link was taken down for maintenance reasons remotely, and the transceiver remained plugged in. So because the model was agnostic to this, we assumed the transceiver was gone because the link was taken down and we had no packet counters anymore, but it was still plugged in and it was still sucking power, which is why it doesn't dip that much on the other two lines. But the fact that the thing remains powered on it doesn't have to be. It's a software problem, and it's something that can and should be fixed. Right? Today, it's clear to us now, I've been working in this area for a while, that the hardware drivers for network operating systems are not written for energy efficiency. It's all about maximizing the speed that they can deliver. The challenge is that it's a kind of difficult to prove that point because we cannot really easily rewrite those drivers, right? Because everything is closed source, we don't have access to the software. It's tricky to modify this. Of course, you could try to do this on an open source operating system such as Sonic. We've tried this. We haven't been very successful in getting that to work so far. So if you have experience in this area, it would be very interesting to hear about advice to proceed. So to close that presentation, I showed you how we followed the methodology we followed to establish the power model and how it can be used to estimate link saving approaches. I would like to conclude with some additional lesson learned over the course of that project. So the first thing is, in most cases, we found that indeed datasheets seems to pretty strongly overestimate the average power that we were measuring from the hardware device, but not always. In the switch network for two router models, the datasheet actually quite seriously underestimate the measured power value, and those routers were not under particularly high load, so it seems really to be a problem from the datasheet itself. The second is that some power supply units seems indeed, as we've been suggesting to us, to be not very reliable. Here is the same plot as before for another device model, where the red curve, so the power supply unit measurement, is essentially a pseudo constant thing, and if you paying close attention, this drop we see here, this big drop in the red curve, coincide with when we started measuring. And effectively what happened is that one of the two PSUs we unplugged, replugged, and it started reporting 7 watt less, while nothing has changed in the state of the router. So that's probably not very reliable. In other cases, we observe power values that changed in sometimes unexpected ways. In that particular example, we have a 10% power increase that is due to an OS upgrade. In practice, what happened is that the upgrade resulted in a different fan control policy that started blowing the fan full blast while it was not particularly necessary. And there are other things we've learned that are not direct consequences from the data we've collected, which is that some hardware models from Juniper, the SerDes line that connect the ASIC to the interfaces remain up all the time, no matter what you do. And that's something that can be fixed, obviously. They actually, in those blog posts, proposed a fix and say that if you in your configuration apply an additional keyword on top of shutdown, then you can actually turn off the service lines. And they show with measurement data that this can save an absurdly high amount of power on those router models. Right, with that, I would like to conclude by drawing your attention on all the artifacts and data that we've made available. I've already mentioned all the tooling necessary to reproduce the power model. You will find under the Fantastic Tool link. The AutoPower project, which is somewhat an independent thing that is designed to let you measure and collect power data from any device you can deploy anywhere. And finally, we've created a platform, it's called the Network Power Zoo, to collect all power-related information that we and others have collected over the course of this project. It is publicly available. You can go there, download all the data you're interested in, and we've built the system to be easy to integrate other people's data. So if you have access to that, welcome to reach out and integrate your data into the dataset. All the links I mentioned here and the paper reference you can find in the description of the video. Thank you.